Hey guys, Mr. Marone here. Welcome back. We are doing today G.co.C.10 notes, and it's the second day of it, so we're going to finish up our discussion on triangles and triangle relationships. And we're going to start out by looking at this idea of the exterior angles of a triangle. So an exterior or an external angle is the angle formed by a side's extension and its adjacent side. And a pictorial example is if I have this triangle, if I extend it out this side, this right here would be my external angle. Right there. And then we have this idea of remote angles. And the remote angles are the internal angles that are non-adjacent to our external angle. So in my same picture there, that's my external angle. Here and here, those are my remote angles. There and there. And then my external angle is right there. So those are the definitions that we're going to use moving forward. And there's a couple different proofs here. The informal proof that you guys will do on your own if we cut out a triangle and we cut out an external angle is that the two remote angles fit perfectly into the external angle. That's what we're ultimately going to hope for. And what I'm going to do is do more of a formal proof here with you guys on this. Okay, so here they've given us a triangle with an external angle, angle ACD, and they want us to prove that that outside exterior measure is going to be the same thing as angles A and B put together. So the first thing that we can do is discuss our idea of a triangle, and we know that that angle A plus angle B plus angle C equals 180 degrees, and all triangles equal 180 degrees would be our reason. Okay, the internal angles of a triangle are always 180 degrees. Okay? We also know we have a linear pair here and here that angle BCA plus angle ACD equal 180 degrees. And that one is a linear pair. Okay? Since I have 180 degrees here and here, I can substitute in and say that angle A plus angle B plus angle C equals angle BCA plus angle ACD. Okay? And what is important to notice is that angle BCA is the same thing as angle C. This was our substitution. Sorry about that. Or the transitive property, whichever one you prefer. And as we notice, angle C and angle BCA are the same thing, so we end up being able to subtract those, and we get angle A plus angle B equals angle ACD by our subtraction property. Okay, so there's a more formal proof of what we're looking at here. And just as another one so you guys see it, we're going to do a transformational proof as well. And what I'm going to do here is I'm going to translate the triangle that they gave me by the vector BC, so along its bottom line here. Okay, and I'm going to translate it out so we end up with a figure that looks something like that. Okay, and I have A prime up at the top, and I have C prime out here, and B prime is the same thing as C. So we're going to translate triangle ABC by vector BC. Okay. And we know that translations preserve angles. So we have that angle ACD is equal angle AC A prime. Okay, so ACD is the same thing as AC A prime when we do that transformation there. And we also know that it's ACA plus angle ACC prime. We also know that angle B is congruent to angle ACC prime, and we know that angle A is equal to angle ACA prime. Those are the same. So because we can say that because we have alternate interior angles, due to the fact that when we do a translation, we end up with parallel lines here at AB and A prime C. And when we substitute all of that in, we end up that angle ACD is equal to angle A plus angle B. So a bit more involved, a little bit less straightforward than our regular proof there, but still something worth looking at. So now I want you guys to try some using the idea of exterior angles and those angle measures. See if you can come up with answers to these 3 questions, and then we'll come back. I'll unpause the video, and then you can check those answers with mine. All right, welcome back. Hopefully you were able to find all of these same answers that I was able to find. That in part A, angle BCD was 147 degrees when we combined those two remote angles. For letter B, that you got angle B was 44 using our exterior angles theorem, and that angle BCA, the third angle of the triangle, was 115. I did that by using a linear pair here. And I did the same thing in part C in order to find that third angle. And I found that angle A was 122, and then BCA was 20 degrees in our third problem. So that wraps up the idea of exterior angles in triangles. And our last thing that we're going to cover is something called the mid-segment theorem. Okay? And what I'm going to do is perform an informal proof, or use some transformations here, and show it this way. And then there are a couple in your notes that we are not going to talk about. Okay, so I'm going to start out with this figure by translating triangle ABC by 2 vectors. We're going to move it upwards, and we're going to move it across AC as well. So we've got 2 new triangles there, and we know that now that I've got B prime up here, that this allows me to say that B is my midpoint of A, B prime. So that tells me these 2 are the same. So if I translate triangle ABC by vectors AB and AC, that tells me B is the midpoint of A, B prime. And we also know, if we're looking closely at this, if I call this point D and this point E out here, that D is the midpoint of these 2 segments out here. So D is the midpoint of B prime E here. So I now know that those 2 are congruent. We know from our understanding of transformations that BD, this new segment up here, is going to be parallel to AC. Right? Parallel is what happens when we translate. Everything stays parallel. And we also can tell here that by sliding it up and then sliding over like we did, that AE, that new length at the bottom, is going to be equal to 2BD. Okay, so it allows us to say that it takes 2 of this top segment to create our lower segment. And this last piece here, that AE equals 2BD, this is a really, really important thing for us. This is really what we're getting to the heart of with our mid-segment. So a mid-segment is 2 midpoints being connected together, which we talked about here. B and D are both midpoints. So that's going to be the mid-segment of our big triangle AB prime E. And this mid-segment has 2 really distinct properties. It's going to be parallel to the base of the triangle, and it's also going to have to take 2 of that mid-segment to create the actual base. So those two things work hand in hand, and they're really important for us as we move forward. So I've got some that I want you guys to try. Okay, the first one's right here. We're just using that idea that our midsegment, it takes two of them to create our base. So make sure that you are using that as you go to solve these problems. I'm going to pause the video and let you guys try these, and then when we come back, all the answers will be there for you to review. All right, so when you come back, you should notice that the first one, our midsegment was 13.5, so the base is going to be double that. It's going to take two of those to create our base, so we got 27 there. In our middle one, it takes two of that midsegment to create the base, so I have to double 3x to 6x and then solve out. So we end up with x equals 7 there. And in our final one, we notice we're trying to solve for a missing angle. Since the other big crucial part is that our midsegment is parallel to the base, that allows me to have corresponding angles in those two corners right there. And that allows me to say that x equals 68 degrees because of those corresponding angles. So I've got a couple more that I want you guys to try, and then we will wrap up our discussion here. So there's the first three, and then the second three are below it. So I'm going to encourage you to try all 6 and then unpause this video and we will review those answers. All right, welcome back. So when we look at our first figure there, it shows us that 8 and x both have 2 tick marks. So those are going to be equal. Remember, with a midsegment, this point here is a midpoint of this right-hand segment here. So that does split the figure into 2 congruent parts. To find y, we know that the midsegment is half the length of the base, so I would divide 18 by 2 to get 9. In our second one, we have corresponding angles. That gets me x. And if my midsegment is 7, I have to double it to get my base at 14 centimeters. In my last one, if my whole base is 18, that means that my midsegment x is going to be half of that. And if we look closely, if we were to turn this figure, y is the midsegment of this whole segment here, and y and 8 have the same measure because it takes double of that to create our base. So y would equal 8 in that example. On our bottom three, once again, we have corresponding angles between x and 86. And in order to get y, that's the midsegment of this figure. If the whole base is 24, we would cut it in half to get y. In our middle one, our midsegment is 8, so the base is double that to 16. And to get y, we have an isosceles triangle here. So those two base angles are the same, as we remember. And 70 and 70 together is 140. If we did 180 minus 140, that gets us our vertex angle of 40 degrees for y. And in our last one, in order to find our x, 9 was my midsegment, so x would be double that to 18. And then to find y, we have to do a little bit of extra work. This little triangle up at the top is actually a Pythagorean triple. So I've got my two legs here, and we can use Pythagorean theorem and say that 9 squared plus 12 squared equals, we'll call it z here, z squared. And when you solve out, you get 225 equals z squared. And taking our square root there, we end up with z equaling 15. Y they wanted was the whole length here, so we would have to double that to get 30 degrees, or 30 centimeters there. Okay. So this evening, I want you guys to try out the homework for this section. There's a lot of problems with exterior angles and with midsegments that we can try. So I hope you guys find this useful and bring in any questions you have into class tomorrow.